Hello, and welcome to Sound. Let us start with the question, what is sound? Sound is a wave generated by oscillating particles, such as air. Sound is longitudinal, meaning that it pulses out from a source, like so. A transverse wave is different. It only moves in one direction, like a wave in the ocean, or a wave moving down a stream. Also, in a longitudinal wave, the particle displacement is parallel to the direction of the wave. In a transverse wave, the particle displacement is perpendicular to the direction of the wave. How do speakers work? Speakers are humans that go out in public and present ideas to a crowd verbally. Sorry about that. Audio speakers create sound by translating digital signals into movement. These oscillations push air back and forth, creating sounds. Parts of a speaker include a cone, a permanent magnet, and an electromagnet. By turning on and off the electromagnet, the force of attraction between the two magnets changes, moving the speaker, and thus creating sound. Properties of waves. Let's discuss the properties of waves. Waves have an amplitude, which determines the volume of a sound, a wavelength, a frequency, which determines the pitch of a sound, a velocity, and a period, which is the time it takes for one wavelength to pass a fixed point. The velocity of a wave is determined by the function of its wavelength times its frequency. The period of a wave is determined by the equation of 1 over its frequency.
Please don't be alarmed.
Quick, name the 5 properties of waves before the Harlem Shake drops. Quickly! Quickly! Did you get all 5? Here they are again. Amplitude. Frequency. Wavelength. Velocity. And period. 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 Interference. Hello, this is producer Fred here to talk about interference. Alright, so a common problem with sound and waves is interference. There are 2 types of interference. When 2 waves of opposite phase, meaning a trough of one wave and a crest of another, interfere at the same time, the result is destructive interference. Therefore, the resulting wave's amplitude, which is the volume of a sound, will decrease. If 2 waves are in the same phase, meaning 2 troughs or 2 crests interfere at the same time, the result is constructive interference, and the amplitude will increase. Alright, now since this is the 10th time I've tested this video, I forgot what I was talking about. Anyway, let's see what we're doing. We're doing right. We're doing interference. Interference. All right. All right. So here's a kick sample. You can see the sample right here. Right. I think my software is very slow at detecting this, so I'll make slow mouse movements. Alright, let's drag that into the playlist right here. First, I'll show you constructive interference. If I layer these so that the waveforms are exactly the same on top of each other, then we get a higher amplitude. Ah, that was terrible. That sounds terrible. Here's with just one. Let's add another. Yeah, you get the idea. Alright, let's duplicate this kick. And let's reverse one of them. Reverse. Wait, no, not reverse. It's reverse polarity. I don't know if you see that button right here. But there's a button that says reverse polarity. Alright, that was a pain. So I had to just get a different sample, I guess. So here's a snare sample, and it's kind of hard to see, but here's a duplicate of it, and I did the reverse polarity thing on it, and now since they're lined up, I don't know if you can see the waveforms. Let's see if I can zoom in. Let's do that. See how one of them goes kind of up and the other one down? One of them is reversed. So now when I play them together, what happens? They cancel out completely. Let's mute one of them. Now let's mute the other. See, it's the same thing. Yeah, destructive interference. Alright, let's discuss pure versus complex tones. So when someone says a frequency is a certain hertz, like say 440 hertz or something, they're talking about either the fundamental frequency of a tone or just the tone itself. Now, a sound that is just 440 hertz is really boring, because as it's a pure tone. And to show you what pure tones look like and sound like, I will create one for you. So I have a synthesizer open here, and with just one oscillator, with a sine wave and one voice, and here's how it sounds. Now wait, hold on. Gotta initialize everything. Initialize sine wave. Alright. Those are pure tones. Let's see if I can analyze them. I'm not sure how well you can see this, but here is a paragraph equalizer that's displaying what tone is being played. So if we play this, let's throw in something. Here's a G sharp 4. I don't really know what frequency that is, but I can tell if I look at this. It might be hard to see, but here I can see which frequency. It looks about 208 hertz or so would be a G sharp 4, just based on my analysis. But if you look at the equalizer, let me just mute this so it doesn't sound boring. See, as it's playing, you can see that this is just a pure tone. There's one frequency playing. Now if I were to use a different type of wave, let's see how that sounds. It's called a saw wave. It has a fundamental frequency which is the same tone as before, as well as many other tones, other harmonics that create that sound. Yeah. Now let's take a look at even more complex tones. Let me open a synthesizer or whatever. Massive. As you can see, there are a lot of different frequencies in this one sound. There's a lot of mid frequencies, between about 500 and 1,000 hertz. There's a resonance at about 250. There's some bass in it and some random other stuff that make up the sound. See, complex tones, which create most sounds we hear, are actually just a bunch of different frequencies blended together to create a different type of sound. And the number of frequencies that a sound could use are almost endless. If I were to, here's a drum loop I found. It sounds very simple, but if we were to look at what frequencies are actually playing, you can see pretty much the entire spectrum is filled at one point or another. A snare, the snare sound, let's see if we can isolate the snare sound. See, the snare sound is very involved in terms of which frequencies they're hitting. There's a fundamental frequency, of course, as every sound has. They tend to be lower. This one's about 180 hertz, but it's got a whole wide variety of frequencies above that, which create the timbre of this snare.